Alright kiddos, we're back, and we're going to continue to talk about shape, bond angle, and polarity, as well as drawing lots and lots of Lewis structures. Hope you're excited about that. I thought we'd start with this picture here of balloons representing pairs of electrons. This first set represents a central atom with 4 pairs of electrons stuck to it. So I'm going to put one pair up here. This pair goes back into the paper. I know that's hard to envision, but this one does as well, so they represent these 2 balloons here. And then this one here is coming out of the paper at you. And that represents, of course, that balloon right there. Now, the angle here, folks, if you remember, is 109.5 degrees. Between any 2 pairs of electrons, it's 109.5 degrees. Now, if all 4 of these pairs are bonding pairs, 1, 2, 3, 4. So we've got 4 atoms bonded to it. We call that a tetrahedral shape, and the angle is a nice, pretty 109.5 degrees. However, if only 3 of those are bonding, so let's get rid of this one up here, and let's just make that a lone pair of electrons here. We now no longer have a tetrahedral for our molecular shape. We have this trigonal pyramid shape. Can you see it? And the angle is actually a bit less than 109.5 degrees. Then we can end up with only 2 pair being bonding. So let's get rid of this guy down here and replace that with a lone pair. And so now you can see the shape would be bent, wouldn't you? Would be bent between those 2 atoms, and the angle would be, once again, a little more than 4 degrees less than 109.5 degrees. So those are the options when you have 4 pairs of electrons around your central atom. Now, what if you have 3 pairs? And we're going to see that today. If we have 3 pairs as far away from each other as possible, we'd have this, then this, and this. They could all lie flat on a plane, and the angle would be exactly what you would expect, 120 degrees. 120 degrees. Now, what if we have all 3 of them bonding? Okay, well, the electronic shape and the molecular shape would both be trigonal planar. If only 2 are bonding, so let's get rid of this one here and replace that with a lone pair. Now we would have a bent shape, kiddos. And the angle would be a bit less than 120 degrees. And then finally we end up with 2 pairs around our central atom, and you can imagine with 2 pairs as far away from each other as possible, we are going to end up with a bond angle of 180 degrees, and we call that a linear shape. So if both of those are bonding, we would have a linear molecule, and the bond angle would be 109.5 degrees. So let's go ahead and see which of these above are related to the electron pairs surrounding the water molecule. We were working with that towards the end of our last video, so let me redraw the Lewis structure for you. We have oxygen sharing a pair with 2 hydrogens, and then 2 lone pairs around the oxygen to complete its octet. And so, if you take a look, don't we have 1, 2, 3, 4 regions of electron density? So that's going to be related to this shape over here, isn't it? So we would say that this is related to a tetrahedral electronic geometry. How many of those are bonding regions? Well, just those 2 are bonding, and these 2 pairs here are non-bonding. So now we have to figure out the shape. So if I were to use my balloon model here, here's the center. There's one above, non-bonding. This guy goes into the paper, remember. This guy goes into the paper, remember. And this one comes out of the paper, and it's a non-bonding pair. Can you see that the shape of the water molecule, if we just consider the hydrogens and the oxygen, it's not linear. It is bent. And what would you expect the bond angle to be between this hydrogen and this hydrogen? And if you said 109.5, I wouldn't argue with you too much, but it's actually going to be closer to 105 degrees because these non-bonding pairs, remember, take up a bit more space than bonding pairs. What about the polarity of that molecule? Well, let's use our spaceship analogy for that. Here's our oxygen in the center, and we have a hydrogen pulling this way, a spaceship pulling that way, and another hydrogen pulling this way. Is that oxygen in the middle going to move? You bet it is, because remember, even though we have things up here and here, there's nothing attached to them, so they're not pulling to cancel out the dipoles. So this would be a polar molecule. Water is polar. All right, let's try a few more. And we're going to start with an exception to the octet rule. Boron is an exception. It only needs 3 pairs around the central atom to be stable. We won't talk about why for right now, but just know we listed it earlier. It is one of our exceptions. So to draw the Lewis structure for BF3, we have 1 boron atom and 3 fluorine atoms. Let's see how many valence electrons each of those have. Here's boron in group 13, so it has 3 valence electrons, and here's fluorine over here in group 17. It has 7 valence electrons. So 7 valence for each fluorine, 3 valence for each boron. So we have a total of 3 and 21. That gives us 24 valence electrons to work with here in drawing our Lewis structure. Let's put boron in the center, and nature does tend to be symmetrical, so we'll stick 3 fluorines on it, and then we'll give each fluorine an octet. So we'll put 3 more pairs around each fluorine. And we're going to leave boron alone because remember it's an exception to the octet rule. So how many electrons have we used of our 24? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yeah, we've used up all 24, so that's great. Now how about the shape of this? Well, let's take a look at our balloons. Don't we have 3 regions of density here around the boron atom? So it looks like that's going to be trigonal planar. Trigonal planar. I know it looks like a T to you, but remember the boron's in the center, and we have these 3 pairs coming off. They are 120 degrees from each other, folks. So that bond angle is an expected 120 degrees. How about the polarity? Well, we've got a spaceship pulling this way on the center boron, a spaceship pulling this way, and a spaceship pulling up. Aren't they all going to cancel each other out? You bet they are. So this would be a non-polar molecule. All right, let's do some more. We're on a roll here. OCl2, oxygen. There's 1 oxygen. Chlorine, there are 2 of those. Let's figure out how many valence electrons each one has. So here's oxygen, kiddos. It's in group 16 of the periodic table, so it has 6 valence. Here's chlorine in group 17 with 7 valence. So 6 valence for my oxygen and 7 valence for each chlorine. So we get 6 plus 14. Looks like I'm allowed 20 valence here. We'll put oxygen in the center, and we'll put a chlorine to either side. We'll complete oxygen's octet and chlorine's octets. And count them up and see how many of you've used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yeah, we've used our 20 valence. Great. So let's look at the center atom to figure out the shape. Do you guys see that there are 4 pairs around the center atom? So let's go back a page. When we had 4 pairs, isn't that our tetrahedral electronic geometry, this guy right here? And so I'm going to draw this. We have a pair up here that's not bonding. This chlorine's going back into the page. This chlorine's going back into the page. And this non-bonding pair is coming out of the page. So if we look at the shape, it looks like this guy is going to be bent. And how about the angle between these chlorines? Now if you said 109.5, I wouldn't lose too much sleep over it, but it's really closer to 105 degrees. How about the polarity? Well, there's a spaceship pulling this way on that oxygen, and a spaceship pulling this way. They're at an angle to each other, aren't they? So they don't cancel out. So that would be a polar molecule. All right, let's do another one. BeF2, Be is another exception to the octet rule. It's satisfied with 2 pairs of electrons around the center atom. So let's go ahead and keep that in mind as we draw the Lewis structure for BeF2. So let's figure out how many valence we're allowed. There's a beryllium and 2 fluorines. So let's find beryllium on the periodic table. It's way over here in group 2, and we've already found fluorine earlier. It's in group 17. So 2 valence for beryllium, 7 valence for each fluorine. Looks like we have 2 plus 14. Looks like we're allowed 16 valence electrons in my Lewis structure. Put beryllium in the middle, bond a fluorine to each side, and then we'll complete fluorine's octet. Remember, beryllium, we said, disobeys the octet rule. It's satisfied with just 2 pairs around it, which is what we have. So how many total electrons are we using? 2, 4, 6, 8, 10, 12, 14, 16. Good. 16 is what we're allowed. So let's see. The shape of this guy, we have an atom in the middle, a fluorine, and another fluorine that is as far away from each other as possible. That's linear. Bond angle for that one's easy, 180 degrees. And then the polarity, we have a spaceship pulling this way and a spaceship pulling this way with the exact same amount of strength. Is this beryllium in the middle going to go anywhere? Nope, it's not. So that guy is nonpolar. Okay? All right, CF4. CF4. So we have 1 carbon and 4 fluorines. Now let's find out how many valence electrons carbon has. Here's carbon, kiddos, in group 14. So 4 valence. And we've already used fluorine a couple times. It has 7 valence. So 4 valence for my carbon, 7 valence for each fluorine. So we have 4 and 28, 32 valence. 32 sounds like a pretty number. Well, let's draw this Lewis structure. We'll put a fluorine on all 4 sides. Notice that completes carbon's octet. And then we'll complete the octet around each fluorine by giving each fluorine 3 more pairs. And count them up. Guess how many electrons we've used? That's right, we've used 32. So the shape of this, let's see, there's my carbon in the middle. We have a fluorine up top, 1 fluorine going back into the paper, another one going back into the paper, and then another one coming out of the paper. So the shape of that is tetrahedral. And the bond angle for that, kiddos, is a nice, pretty 109.5 degrees, isn't it? Alright, so let's figure out the polarity. We have a spaceship pulling that way, out of the paper here and here. Is that carbon in the middle going to go anywhere? It's not. So this guy is also nonpolar. Okay, I think that's enough for this video. We'll do a bunch more in the next video. Lots of practice. That's how we're going to get good at these. So we'll talk to you soon. Bye-bye.